Hi, this is Tzvi Rosen. Today we're going to talk about integration strategy and improper integrals. That corresponds to sections 7.5 and 7.8 in Stewart's calculus. First we'll go over strategies for integration, and this is section 7.5 in Stewart's calculus. And this section is all about putting together all of our tools that we've accumulated so far for integration. So first of all, we have the set of standard antiderivatives. Think, the power rule for x to the n. We know what the antiderivatives are for the trig functions, cosine x, sine x, secant squared x, and secant x tan x. Or the exponential function obviously is its own antiderivative. Those are our standard antiderivatives, and they're the most basic tools in our toolbox. The next is u substitution, which comes in handy in a bunch of cases. Integration by parts, which we studied in 7.1, which is great for products of functions. Trigonometric identities come in handy when trying to integrate things like sine to the mx, cosine to the nx, or secant to the mx times tan to the nx. We also have trigonometric substitution, and that's where we plug in a function like a sine theta, a secant theta, or a tan theta for our variable x, and that helps us simplify radicals. And finally, we have partial fractions, which are good for rational functions, those being quotients of polynomials. And here's a little flow chart that might be helpful, and we'll zoom in here so you can see it more clearly. So when we approach an integral, our first question should be, is this a standard antiderivative that I can just plug in the formula? Okay, if not, we'll try to apply u substitution. Is there some way to simplify the integral via u substitution? If that's the case, then we make the substitution, and we have to be sure that when we do that, we also change the differential by using du equals du dx times dx. Okay, but if we can't simplify it via u substitution, the next thing we check is, does this have the form sine to the mx, cosine to the nx, or secant to the mx, tan to the nx, where we can use a trig identity to simplify it to the point where we can do a u substitution. Is the integrand, okay, but if it's not in that special form, we'll check, is the integrand a rational function? If that's the case, we'll use partial fractions to break it down into easier integrals. If it's not a rational function, then we'll check if it's a product of functions, or if it involves, or if it's a function that has a simpler derivative than it has an antiderivative, for example, ln of x. And if that's the case, then we'll try integration by parts. If that's not the case, then we'll look for things like 1 plus x squared, or x squared minus 1, or 1 minus x squared that can benefit from trig substitution, and we'll try a trig substitution. If none of those things work, then we should try manipulating the integrand using trig identities, or playing around with fractions, multiplying numerator and denominator by something, doing something to change the integral into something that we can actually do. So those are our strategies. And let's see those in work. Let's see those in action. So first example, 1 plus the square root of x to the 8th power dx. So when we're looking at this, we could, if we wanted to have a bad time, we could go ahead and multiply it out and say, okay, well, 1 plus square root of x to the 8th is 1 plus x times 1 plus square root of x times 1 plus square root of x times 1 plus square root of x, etc. We don't want to do this. Okay. It'll just be a lot of multiplication and generally annoying to do. So instead, we'll see if we can do a u substitution for 1 plus the square root of x. Because if that were the case, then we would have u to the 8th, and it would be much simpler. Well, if u is equal to 1 plus the square root of x, then du is equal to, okay, obviously the 1 vanishes, and x to the 1/2 becomes 1 over 2 root x dx. Okay. Well, 2 root x can also be written as 1 over 2 times u minus 1, because u is 1 plus the square root of x. Okay, and that means that 2 times u minus 1 du is equal to dx. Given that, we now have our integral becomes the integral of u to the 8th times 2 u minus 1 du, which is 2 times the integral of u to the 9th minus u to the 8th du. And applying the power rule, now because this is a standard integrand, we have 2 times u to the 10th over 10 minus u to the 9th over 9. And we want to make sure that we include a constant of integration. And we still have to turn back into our original variables. We start out with u equals 1 plus the square root of x, so this becomes 2 times 1 plus the square root of x to the 10th power over 10 minus 1 plus square root of x to the 9th power over 9, and we can pull the constant out if we'd like. And this is the antiderivative for this example. Okay, here we use the u substitution to simplify it into a standard antiderivative. Now let's look at this example. We have ln of x plus 1 divided by x squared dx. Okay, so the first thing I always want to try, if it's not a standard antiderivative, which we can see it's not, is a u substitution. But a u substitution here, we could try x plus 1, and we could try ln of x plus 1. But in both of those cases, it doesn't look like the u substitution will work. So let's make a note of that. U sub does not seem possible. Okay. Obviously, it's not in the form of a trig integral, and it's not a rational function since the numerator is log. So let's try integration by parts. Okay, so we're going to have, we always want u to be the earlier one in Lie8, right? So we have log is the first letter in Lie8. So we take u equals ln of x plus 1, and dv equals dx over x squared. Okay, well, we know how to integrate this using the power rule. It's x to the minus 2, so this becomes minus 1 over x. And du is 1 over x plus 1 dx. Okay, that's our integration by parts. So our integral becomes uv, which is minus ln of x plus 1 over x. And we subtract the integral of v du. Well, because v has a minus sign, we can make this a plus sign. And we have 1 over x times 1 over x plus 1 dx. Okay. So this is already much nicer. This is a rational function. Okay. So we're going to try partial fractions. So the first thing we do with partial fractions, we check that the degree of the top is smaller than the degree of the bottom, which is true. And then we factor the bottom, it's already factored, and we set up the correct form, which in this case it's distinct linear terms. So we get a over x plus b over x plus 1. Okay, now we clear denominators and set them, and we obtain 1 equals a times x plus 1 plus b times x. Okay, this means that a equals 1 and b equals minus 1. Okay. Okay, so using what we just obtained from the previous page, so right now we're trying to solve the integral of 1 over x times x plus 1 dx. And we found that this is equal to the integral of 1 over x minus 1 over x plus 1 dx. And this is ln of x minus ln of x plus 1 plus c. Okay? And plugging that into the integration by parts formula we find that the original integral, which was integral of ln x, ln of x plus 1 divided by x squared dx will be equal to minus ln of x plus 1 over x plus ln of x minus ln of x plus 1 plus c. Okay. So here, just to review, we started with integration by parts. We obtained something for which we used partial fractions, and putting it all together, we found our integral. We'll do one final example. This is the integral of sine x cosine x divided by sine to the fourth x plus cosine to the fourth x dx. Okay, so there's a very trig flavor to this integral, so we're going to try to use some trig identities. Looking at the bottom here, we notice that this would be really great if it were sine squared x plus cosine squared x, because that would be equal to 1. But we have sine to the fourth x plus cosine to the fourth x. So how can we get from this identity to this denominator? Well, if I square both sides of this equation, I'll get sine to the fourth x plus 2 sine squared x cosine squared x plus cosine to the fourth x equals 1. And then we have the two parts of the denominator. We're just missing this. So if I move that to the other side of the equation, I have sine to the fourth x plus cosine to the fourth x equals 1 minus 2 sine squared x cosine squared x. Okay. Well, that's useful because this is very close to the top. So let's rewrite the integral in terms of that. So we have sine x cosine x divided by 1 minus 2 sine squared x cosine squared x dx. Okay, the next trig identity I want to use is the double angle formula, because when we have a product of sine and cosine, we recall that sine of 2x equals 2 sine x cosine x. So this is equal to, in the top we have 1/2 of sine of 2x. And in the bottom we get 1 minus, well, if we were to square both sides of this equation, we get sine squared of 2x equals 4 sine squared x cosine squared x. And so if we want 2, we'll just multiply that by half. We have 1 minus a half of sine squared 2x. Okay, simplifying the fractions, we get the and dx, of course. We get the integral of sine of 2x divided by, and now we've distributed the 2 minus sine squared of 2x dx. Okay. Now, I don't love having this 2 here. And also, it's not great to have the sign in the bottom and the sign on top. Ideally, we would be able to do a u substitution, turning so that we can make u equals sine. Then we would have du equals cosine. So there's still some manipulation we want to do here. I'm just going to box this off. Okay, so let's make a new slide. So now we're at sine 2x divided by 2 minus sine squared 2x. Okay, and again, we want to figure out a way to make the bottom a cosine. So let's remember that sine squared plus cosine squared equals 1. So 2 minus sine squared of 2x, that's equal to 1 plus 1 minus sine squared of 2x, which is just equal to 1 plus cosine squared of 2x. Okay, so let's plug that in. And now we have something where we could make a u substitution. If we do a u substitution for cosine 2x, the du is 2 sine 2x dx, right? So let's make this, let's make this u substitution. U equals cosine of 2x. Du equals 2 sine 2x dx. And so we get 1/2 on top, 1 plus u squared du. Okay, and we recognize this integral. This is the integral that gives us arctangent. Okay, so we have 1/2 arctangent of u plus c. And because we had u equals cosine 2x, this becomes 1/2 arctangent of cosine 2x plus c. And here you might start trying to draw right triangles to figure out if there's any way to simplify this relationship, but it turns out this is the simplest way to express it. This cannot be further simplified. So this is an example of an integral where we started with applying all of these trig identities until we got something where we could do a u substitution, and then we found an integral which we knew how to do. Okay, so there's all sorts of ways to do these integrals. The key is to check every tool in your toolbox and start with the easiest first. So start with the integrals you know, u substitution, and then move to your more complicated tools. And we should also note that not all functions have elementary integrals. For instance, the functions as simple as e to the minus x squared, e to the x over x, cosine of x squared, and 1 over ln x have integrals that cannot be expressed in terms of elementary functions. That's not to say that the integral doesn't exist. Okay? The integral exists, but we don't have a simple way of writing it down besides just the integral. So for instance, f of t equals integral from 0 to t of e to the minus x squared dx. So when you find an integral out in nature, there's a very good chance there's no nice formula for it, but you're still able to approximate it. It's a function that does exist. In terms of the problems you'll receive in this class, they'll all be problems that you can actually integrate. Section 2 of the talk is improper integrals. What makes an integral improper? Well, there are two types of improper integrals. The first type is where we have infinity or negative infinity in the bounds. The second type is where the function has an infinite discontinuity somewhere in the bounds. Okay, whether it's in the bound precisely or somewhere in between. For example, the integral, this is an example of the first type, integral from minus infinity to infinity of e to the minus x squared dx. So there we have both negative infinity and infinity in the bounds. The integral from 1 to infinity of 1 over x dx is also an improper integral of the first type because we have infinity as the upper bound. For examples of the second type, we have integral from 0 to 1 of 1 over x dx. Here we know that x equals 0 is an infinite discontinuity for this function, so that makes it improper. And the other integral example of the second type is integral from 0 to 3 pi over 4 of tan x dx. We know that tan x has an infinite discontinuity at pi over 2, and since that's in the bounds, the integral is improper. So let's talk convergence and divergence for improper integrals of type 1. And what we're really curious about is how do we make sense of an area extending to infinity? What does that even mean? We usually think about area in terms of something that we can put our hands around. So what do we mean when we talk about an integral going off to infinity? So here's what we mean. We're talking about the area under the curve y equals 1 over x from x equals 1 to x equals t. And that's the integral from 1 to t of 1 over x dx. That's a function of t. It's a function of the upper bound. So for example, in this image, the function has input 2. That's where we're putting in the upper bound, and we'll get out a number which corresponds to the area. For the input here, we're inputting the number 3, and we're getting the area 2/3. When you input the number 5, you get out the area 4/5. And when you let that upper bound go off to infinity, you put in higher and higher values of t, you're going to get an area that approaches 1. Okay? Like any other function of t, we can compute the limit as t goes to infinity. If this limit exists, we say the integral converges. If the limit does not exist, the integral diverges. Okay, let's look at one example. We already saw this integral as one of the first examples. When we're trying to compute this as an improper integral, we want to first express it as the limit as t goes to infinity of this integral, the integral from 1 to t of 1 over x dx. Okay? Now we know how to integrate this function to do a definite integral where this is some finite value, so we'll just do the integral like normal. This is the ln of absolute value of x, and we're evaluating it from 1 to t. That's going to be equal to the limit as t goes to infinity of ln of absolute value of t minus ln of 1. Okay, we know that second term is 0, so this is just limit as t goes to infinity of ln of t. Since it's positive, we don't need the absolute value signs. And this goes off to infinity, which you can just think about because it's inverse to the exponential function. As t gets bigger and bigger, you can get as large a value of the log as you want. Okay, so this is infinity. So we say that the integral diverges. Okay. Let's do another example. And here we're doing 1 over x to the p dx for p not equal to 1. So here we should keep in mind that whenever p is not equal to 1, this is x to the minus p. And so the indefinite integral is given by x to the minus p plus 1 divided by minus p plus 1 plus c. Or we could also write this as 1 over 1 minus p x to the p minus 1 plus c. Okay, that's just if we want to put x in the denominator. So let's compute this as a limit, as we did in the last problem. So we're writing limit as t goes to infinity of the integral from 1 to t of 1 over x to the p dx. And as we just computed on the right-hand side, that's given by the limit as t goes to infinity of 1 over 1 minus p x to the p minus 1. And we can ignore the constant because this is a definite integral from 1 to t. And this is given as limit as t goes to infinity 1 over 1 minus p t to the p minus 1 minus, and you plug in x equals 1, you get 1 over 1 minus p. Okay. So now the question is, what is this limit? Okay. Well, t to the p minus 1, if p minus 1 is positive, then this denominator gets bigger and bigger. So the fraction as a whole goes towards 0. Okay, then it converges. To minus 1 over 1 minus p, which is the second term. And, or rather, we could also write that as 1 over p minus 1. And if p minus 1 is less than 0, then that means the denominator is getting smaller and smaller, which means the fraction is getting bigger and bigger and diverging to infinity. Okay? So here we've kind of solved a bunch of integrals at once. Integral from 1 to infinity of 1 over x to the p dx for all p not equal to 1. And since we solved for p equals 1 on the last page, now we know that if p is greater than 1, it converges to 1 over p minus 1. And if p is less than or equal to 1, then it diverges. Okay. So now we want to consider the case where the integral goes from minus infinity to positive infinity. So it includes infinity in both bounds. So by convention, these must be computed as two separate limits, i.e. the integral from minus infinity to infinity of f of x dx is equal to the integral from minus infinity to a of f of x dx plus the integral from a to positive infinity of f of x dx. And here we want to take two separate limits, the limit from t to, as t goes to negative infinity of t to a, integral from t to a of f of x dx, plus the limit as s goes to positive infinity of the integral of a to s of f of x dx, where a takes any convenient value. Okay, often you'll put in a equals 0 because that's usually easy to evaluate a function at. The reason that we do this instead of just saying let's use one variable t and let it go from minus t to t, and we'll just take the limit as t goes to infinity, and that'll catch it on both sides. The reason we don't do that is that cancellation can make an integral seem convergent when it shouldn't be. And the example of that, suppose we allow this integral from minus infinity to infinity to be expressed as the limit as t goes to infinity of the integral minus t to t f of x dx. Then if we take f of x equals x, which obviously looks like this, oops, should go through the origin. Okay, and if we're thinking about the area under this curve, so this is, or oops, that's not the area under a curve. So this seems to be a huge area that you have a huge amount of negative area on the left and a huge amount of positive area on the right, and you wouldn't think of those as canceling each other out. But if you were allowed to take a limit like this, as you can see here, you would get x squared over 2 from minus t to t, and that would cancel out to give you 0. So because we don't want a phenomenon like that to happen, we require that you fix a point in the middle and you take two different integrals with two different limits. Okay, so let's do an example like that. We're taking the integral from minus infinity to infinity of 1 over 1 plus x squared dx. Okay, so as we said in the last slide, we need to separate this into two limits. So I'll split it up at 0. So we'll have limit as t goes to minus infinity of the integral from t to 0 of 1 over 1 plus x squared dx, plus the limit as s goes to positive infinity of the integral from 0 to s, 1 over 1 plus x squared dx. Okay. So the antiderivative here, which we should know from our trig substitution days, is going to be arctangent. So we have limit as t goes to infinity, arctangent of x, where x is being evaluated from t to 0, plus the limit as s goes to infinity, arctangent of x from 0 to s. Okay, so this is keep the limit in there, limit as t goes to infinity of arctan of 0, which we know is 0, minus arctan of t, plus limit as s goes to infinity of arctan of s minus arctan of 0. Okay. So, okay, again, this is 0. This is 0. So we just need to compute these limits. So what's the limit as t goes to infinity of arctan? This is something that you can just refer to your chart, your handy trig reference chart, or you can figure it out in terms of a right triangle. This limit is negative pi, oh sorry, this should be to minus infinity. So this will be negative of, because we have the subtraction, negative of negative pi over 2 plus positive, so this arctangent of s, when s goes to positive infinity, you get another pi over 2. So this should be pi. Okay. And we did that taking these two limits separately. And so this teaches us that this converges to pi. Okay, now we can move to type 2. So how do we talk about the area under a curve when the curve goes up infinitely high? For example, if the integrand is discontinuous at the endpoint x equals b, similar to type 1, we're going to treat this with limits. The area under the curve y equals f of x from x equals a to x equals t, i.e. integral from a to t of f of x dx, is a function of t, and we can compute the limit as t goes to b. if this limit exists, we say the integral converges. If the limit does not exist, the integral diverges. There are a couple different cases to consider. Okay, the first is when we're discontinuous at the endpoint. So if f of x is discontinuous only at the left endpoint a, we take the integral from a to b to be given as the limit where t approaches a from the right of the integral from t to b of f of x dx. And the reason it's where t approaches a from the right is because you're computing this integral as you move the left endpoint closer to a. Similarly, if f of x is discontinuous at the right endpoint b, you take the integral from a to b to be the limit as t approaches b from the left of integral from a to t of f of x dx. Okay? And it's the same idea. You're kind of gradually moving that b closer to, you're moving the t closer to b and watching what happens to the integral as you do that. When the discontinuity is at both endpoints, you take two limits. If f of x is discontinuous at a and b, then fix any point c in the middle, and the integral from a to b will be the limit as t goes to a from the right of the integral from t to c of f of x dx, plus the limit as s goes to b from the left of the integral from c to s f of x dx. And let's just draw a quick cartoon of this so that we know what we're talking about. So if we have a and b, and let's say we have discontinuities here, and here's a point c. So what we're talking about now is taking two different limits. So this is our one discontinuity and this is our other discontinuity. We're taking two different limits. One is as we push this integral towards b, and one is as we push this integral towards a. Okay, and that's what we're looking at here. So it's these two integrals. Okay, we can also have a discontinuity mid-interval. So if f of x is discontinuous at b, which is between a and c, it's a similar idea. We take the integral from a to c of f of x dx to be the limit as t approaches b from the left of a to t, the integral from a to t of f of x dx, plus the limit as s approaches b from the right of the integral from s to c of f of x dx. And the strategy is the same as from type 1. We just want to have honest area being measured and not having some weird positive negative cancellation happening. And here's a quick cartoon of what's happening here. So if, let's say this is A and C, and here's B, and we have discontinuity here. And let's say it looks something like this. Okay, so what we're doing is we're computing this integral, taking t and watching as t goes towards b from the left, and then we're taking this integral and watching as what happens to this integral as s goes towards b from the right. Okay, and then we add those together. Okay. So let's look at an example of a type 2 improper integral. So we're computing the integral from 0 to 1 of 1 over the square root of x dx. Well, let's see what happens. So we have the standard antiderivative here. Well, first, where is it discontinuous? So this is discontinuous at x equals 0. And it's not even defined for x, less than 0. So we're really going to be taking limits from the right. So this will be given by the limit as t goes to 0 from the right of integral from t to 1 of 1 over square root of x dx. And now we can use the power rule. This is x to the minus 1/2. So we have limit as t goes to 0 from the right of x to the positive 1/2 times 2. and we're evaluating that from t to 1. Okay, and this is given by limit as t goes to 0 from the right of 2 minus 2 times the square root of t, and obviously this just approaches 2. Okay? So this integral converges to t. Okay, now let's look at this integral. We're looking at integral from 0 to pi of secant squared x dx. So let's think about where is this discontinuous. So we know that secant is 1 over cosine, so this is discontinuous when cosine of x is equal to 0. On this interval, the only time cosine is 0 is when x equals pi over 2. Is the only discontinuity. So what we're going to do is we're going to express this as a limit of two things. Limit as s goes to pi over 2 from the left of the integral from 0 to s of secant squared x dx. And we're going to take the limit as t goes to pi over 2 from the right of the integral of t to pi of secant squared x dx. And now this antiderivative should not be too hard to compute. We know it to be tangent. So we take tangent x evaluated from 0 to s plus the limit as t goes to pi over 2 from the right side of tan x from t to pi. So this will be equal to limit s goes to pi over 2 from the right of tan s minus tan 0, which is just 0, plus limit as t goes to pi over 2 from the right of tan, well, it's tan pi, which is 0, minus tan t. So let's just put a minus sign here, minus tan t. These limits do not exist, right? Because at pi over 2, tangent also has cosine in the denominator. So that goes off to, let's look at a graph of tangent. Okay, so tangent looks like this. Okay, where this is pi over 2. That's minus pi over 2, and this is positive pi over 2, and then it repeats. Okay, so these limits do not exist, so the integral does not converge. I.e., the integral diverges. Okay, and I think we'll end the lecture there. Thank you very much.